so it's a very great pleasure for me to introduce our today's speaker, Zhurun Ji. So she got her PhD from the University of Pennsylvania in 2021, and then spent 3 years as a science fellow at Stanford. And currently she is a staff member at SLAC, but very soon she moves in our region and starts as an assistant professor at MIT. So I believe it will be early in 2026. And obviously in such situation we have to invite Judy because we always want to see new faculty from our area to come to Brown and make connections with us. But there is an even more important reason, because we always want to see rising stars in science. Obviously, Judy is a rising star. She is doing incredible work. But what's particularly exceptional about her, she is a certified rising star because she won a Rising Star in Physics award from Princeton University. Okay, and today she will tell us some of her very nice work on two-dimensional systems. So without further ado, let us welcome Zhurun Ji here.
Today I'm going to talk about, thanks for the nice introduction, Dima, about local microwave probe of multiple different things in the transition metal dichalcogenide systems. And I will do a very unusual start. I will start with the technique. So what we do is the so-called microwave impedance microscopy. And what it works like is like we send in some gigahertz wave onto a tip. And that tip has a very sharp metallic end, and that gives around or less than 100 nanometer spatial resolution. And that gigahertz wave going through the tip goes on the sample, and now the tip and sample has a coupling, capacitive coupling. And that capacitive coupling tells how much the sample springs or how much microwave losses are generated in the process of reflectometry. So for example here, if the sample is very conductive, then all microwave gets reflected back. We get some signal over here. And then if the sample is super insulating, then what happens is the microwave transmits through, and then we get a very sharply contrast signal here. And then so you can see the imaginary part has this monotonic change. And in the middle of the conductivity, that's where we have some contrast of different materials. And we can also look at the real channel. The real channel just measures how much loss is generated in the process of the reflectometry. So if the sample is not a perfect conductor, neither a perfect insulator, then it will generate losses. And in the very middle, the loss is the largest. So that's how we characterize the local electrical properties of the sample using microwave underneath the tip. And this is how our circuitry looks like. This is a technique. We put in microwave. We have all those like cancellation lines and reference lines to do the homodynamic measurement and the amplifier where we get the signal out. And in the part of the input, we have the impedance matching network going on the tip, on the sample, and then get reflected back. So all these parts will be inside a fridge so that the sample is at low temperature and what type of environment we would love it to be. And here's my outline. So using that technique, we would love to do something that usually optical spectroscopies do. So the first thing is the sensing excitonic excitations. And we would also love to do something that usually transport measurements do. So that's the second thing, studying a fractional Chern insulator. So I will start from the first one about excitons. Excitons are photon absorption and generation in many cases. If you absorb a photon, you have extra energy, and now the hole jumps out, and then the electron goes to the conduction band, but because of the Coulomb force, they're bonded together somehow. So that's how the exciton forms. Well, the exciton in two-dimensional materials has been a large testbed of optoelectronic properties, applications, and strongly correlated physics in the recent years. But can we think of excitons as some sort of local sensor of the electrical environment? Well, nitrogen vacancy center has already been used as a sensing agent. because it has these very well-defined energy levels. And then using microwave or optical methods, you can manipulate it, and you can tell the local magnetic field or electric field. But that essence is you have a two-level system. But exciton also has energy levels, just like hydrogen atoms, right? So to explore into that, we first need to somehow sense the excitons locally, especially at low temperatures, and we want to develop a protocol for how it senses other physical quantities, identifying the operation mechanisms, and also develop a readout algorithm. So I'm trying to map onto the way that people do NV sensing, for example. And but then that needs a different technique, right? So because most of the excitonic related studies have been done using optical spectroscopy, and your spatial resolution is limited by the diffraction limit of light. But here, instead of doing that, we shine light through an optical fiber and then focuses onto the metallic tip. This metallic tip sends in microwave and also collects the microwave coming out. So that's the microwave impedance microscopy, but we couple it with an optical fiber. Then what it does is that it can measure the optical coupling or excitation-induced conductivity changes in the sample locally. And if we compare it with of our technique with other techniques of near-field optical measurements, like SNOM, like Professor Dmitry Basov's group, for example, so their lowest temperatures are mostly limited by the optical measurements that they have. But in our case, we can go down to very low temperature and also apply very high magnetic field. So that's once again the advantage of using microwave, because you can use circuits and that's very compact for experimentalists. And also we don't need any metal contact or specific sample surface preparation because of the all-invasive characteristic of microwave measurements. So with this technique kind of intact, we can talk about what are the excitonic 5 features in monolayer molybdenite. So this is an example. It has the A exciton and B exciton, which characterizes the transitions between the two spin orbit splitted bands, and also the 1s, 2s, 3s electrons, the exciton species that corresponds to the different levels, like hydrogen atom-like levels, and they're also bright, dark, charged, neutral, and so on. And here is our result. So if we measure a monolayer TMD system, and then we apply optical excitation. Sorry, this got cut off. So this is the energy of the optical excitation. So 1.6, 2.2 eV. And then the y-axis is the backgate voltage that we applied to this device, or to say this is how we change the carrier density. And upon changing the carrier density, you can tell this microwave impedance microscopy is given some signal that's varying from the red to the blue to the red. And that variation is corresponding to the conductivity variation if you go into the conduction band, the band gap, and the valence band of any semiconductor, right? So that makes a lot of sense. And then if we look into the x-axis, what it means is that at specific excitation energies of light, there are, there are like those like blue region seems to be changing its shape. And that, if we look up and do a one-to-one mapping to the optical measurements, we know that these are the excitonic features. So we are seeing the excitonic features in a conductivity way. And here is how this color map looks like. So red means super conductive and blue means super insulating. And without going into detail of the mechanism of this sensing, we can first compare with previous studies, like when they locally measure the excitons. Yeah.
What do you call the super insulator?
a super insulating.
You mentioned one is superconducting, the other is super insulating. So what do you call a super
Oh,
insulating?
I'm so sorry. I thought superconductive. Like it's like very conductive and very insulating. I'm so sorry for this. Okay, yeah. And then, so room temperature, previous results show this type of excitonic features, which is much wider, and because now we are going down to much lower temperature, so the line width is no longer limited by the phonon broadening, so we can see a very well-defined like dip of this excitonic feature. But yeah, so how it happens, like why can we see this type of conductivity change? Well, usually that's because, so this is our explanation of this result. After the excitons form, they will not always be excitons. There's a specific lifetime of them. And then that's the exciton recombination process. Upon recombination, it's given up some energy. Because of energy conservation, it has to do something. One thing it can do is to knock a hole out of the system. And if that energy is large enough, you can actually let the whole tunnel through the HBM barrier to your gate. And that's called Auger assisted tunneling. And another thing you can do is that electron just becomes a free electron, and that will conduct, and that's photoconductivity. So both processes, one changes the carrier density, the other one changes the conductivity, would give rise to changes of that map. And that results in our so-called optically coupled microwave impedance microscopy signals. But because excitons are very sensitive to the local electrical parameters, like electric fields, conductivity, and permittivity, and so on, because it's a Coulomb interaction and can be affected by the environment, so then we can use the MIM signal as a medium to sense those parameters. So just to give a couple examples, when we change carrier density, the excitons start to strongly interact with the Fermi sea. And that interaction would lead to the splitting of the excitonic resonance into two energies, or more energies. And that energy splitting, which is changing with the carrier density, or the backgate voltage, which is summarized here, is a signature of how much carrier density you have in your system. Another possibility is to sense the electric field. If you have a PN junction, here we have a PN junction formed by a region without backgate and a region with backgate, and that can also just make this whole exciton polariton peak change its characteristic frequency because of the Stark effect. And also the dielectric environment, because it's sensitive to dielectric screening. So if you have a metal very close to it versus having an insulator, it will have different excitation energies as well. So to summarize all this, so what we did was a neural network interpretation of all those experimental results. So we got a whole lot of experimental results with light off with different excitation frequencies of light. And then we go through this neural network to back out all those conductivity and permittivities and so on. And more than that, what we can also do is to compare the excitonic resonance energies or the A1S exciton, and then back out the electric field information. So it turns out that electric field measurement that we had was in very good agreement with what we can get from simulations and other type of things. So essentially, we are operating this exciton as like an MA center or something like that.
Sorry,
Yeah.
On the previous slide,
Yes.
maybe I'm confused. What exactly is the neural network?
Yes.
Is this just for image cleaning, or is it something else?
Right. That's a good question. So this is like a deep neural network that just does the one-to-one correspondence between the MIM signal and conductivity and permittivity. The way that we train it is through a lot of like simulation.
I see.
And that would help us quantify our result. because previously we had that response curve, but we couldn't directly tell like what is the conductivity corresponding to the signal that we got. And here it helps.
So when you train the neural network, you
Yes.
assume that the conductivity is local, right?
We assume the conductivity is
What
local.
if it isn't local?
So the way that we train it is that we assume this is a tip. There is a tip, and there is a sample underneath it, and that's all the things that we give it. If there's a non-local signal, like an edge state or something more complicated than that, then currently this does not capture it. Yeah. So you can only capture the simplest cases.
So when you
For
will
now.
speak about edge states in the
Yeah.
next part of the talk, there will be no neural networks.
There will be no neural networks. yeah. Okay, so I will give a very quick conclusion of this part that we used microwave to sense excitons locally at cryogenic temperatures, and we identified operation mechanisms or tuning knobs of the excitonic resonances, and that helped us developing a protocol or a radar algorithm of the local electrical quantities, not only conductivity and permittivity, but also electric field. So, yeah.
Can you go back to the map that you were showing that has a gate? Right, this one, for example. I'm a little confused that
Yes.
Dark red is maximum conductivity.
Yes.
Why doesn't that happen at zero backgate voltage? Like white, I assume naively that should be backwards. Like zero backgate, you should be in the gap and you should be insulating. Oh, so this is reflecting conductivity of the.
No. Okay. So this is a very complicated case. It's right at the boundary. I guess maybe we can talk about something like this. Then this is inside the bulk of it, and you are asking why this insulating regime is not right at V equals to 0.
So there's an intrinsic doping.
There is intrinsic doping and very large intrinsic doping in the TMD sample. Yes.
Okay.
Yeah. But the overall trend of going through the band gap and going to the other side is still, as expected.
And the asymmetry on two sides of the gap is
Yes.
due to the fact that it's a p-type.
The asymmetry is mostly because of the OJ tunneling process that can only happen for holes, not electrons, in the specific band alignment of HBN and molybdenite.
So does this technique require you to have a band gap for your exciton? So for example, if I have some semi-metal
Right.
or something like that,
Yes.
does that
Yes.
mean this doesn't really work as well?
Yes. I think for a semi-metal it would be very hard because in the background you already get a lot of reflectance of microwave. So you're somewhere here. And even if you excite more excitons, it might not show up very clearly.
Can you speak a little bit about like the transparency of, here you're showing that you have a back gate, but if you were to have dual encapsulation or if you were to have a top gate,
Yes.
would this still work? Or?
That's a great question that I'm going to for
Okay,
the
great.
second part. So yeah. Okay. So if no more question, I will go into the second part of probing the fractional quantum Hall effect or fractional Chern insulators. So that's like we use microwave techniques to mimic what like transport can do. So all the story starts here at Guang University. No, yeah. So the integer quantum Hall effect, and then here with partial filling and non-perturbative Coulomb interaction and low disorder, one gets a fractional quantum Hall effect. So from the edge perspective, the integer quantum Hall effect has slightly easier to analyze edge states because it can remain in a single particle picture. So if we think of a confining potential at the edge, then those Landau levels just bend over, and then at a specific Fermi energy, one can count how many intercepted points are there, and that's how many edge states you have. For nu equals to 2, you might have 2 edge states. And indeed, using like a nanosquid measurement, this has been sort of plotted out that for nu equals to 6, you might be able to count like up to 6. Did I trigger something? Like, yeah, edge states. But for the fractional quantum Hall effect, it's kind of more complicated just because of the strong interaction. So then the picture to explain the edge states would be maybe the Chiral-Latinger liquid or something of the strong correlated models. And then to make it even worse, it has this like particle hole symmetry. So if it is a nu equals to 1/3 edge, it might be just one edge. But then if it is a nu equals to 2/3 state, and if you want to intercept it or like make it adjacent to nu equals to 0, then what it does it goes to nu equals to 1 first and then nu equals to 0, because nu equals to 2/3 can be thought of as nu equals to 1/3 host conjugate state. So all those like hierarchies and particle hole symmetries make studying the edge state of fractional quantum Hall effect more complicated. And then, so over the years, there have been a lot of theoretical models for the nu equals to 2/3 edge, and including the very early Gervin-McDonald picture. For nu equals to 2/3, you have a downstream mode carrying the one quanta conductivity, and then you have another upstream mode that carries 1/3 of it. Then there came the Kahn-Fisher-Polchinski model that talks about when the different edge states strongly scatter with each other, then you no longer have those well-defined nu equals to 1 and 1/3. You have a 2/3 mode and then a neutral bosonic mode going upstream. Then there's the more complicated mirror picture where you break up into 2 downstream modes and 2 neutral modes going upstream, and so on. So this is a small fraction of the theoretical effort to study the edge state. Experimentally, there have been also a lot of things going on, including in the very early days on the gallium arsenide samples, like a Shuri paper here. They measured the magnetoplasma resonance of it. They put on 2 leads and then sent in a microwave pulse. And then essentially they were looking at how much time does it take for this traveling around one loop or several loops of the edge state. So this magnetoplasma or this modulation of carrier density at the edge can give you such type of time-resolved responses. And then later on, there were the noise measurement showing that indeed there is a bosonic mode in their system. And that bosonic mode is in accordance with some of the Kahn-Fisher-Polchinski model. And then there have been the scanning gain microscopy given the conduction stripes. So you can create this type of nu equals to 1, nu equals to 2 type of states in the nanostriction. And that nanostriction, by sweeping the tip around, gives you some conductivity stripes. Then the first one is the edge state interferometry. This has been used more to manipulate the edge state than to study the edge state. But there's where like people want to go into, because I realize and this means that we can really go into the pathway of using fractional quantum Hall states for quantum computing or something of that sort. But yeah, one may ask, like, how to directly image the edge states or the edge physics? Well, then for a traditional fractional quantum Hall effect, usually what you have a quantum wall based 2-dimensional electron gas or 2D material, you have to cool the sample down to ultra low temperature, that's hundreds of millikelvin, and very high magnetic field, around 10 Tesla, for example. And then technique-wise, you need very high spatial resolution, you need to be sensitive to bulk edge differences, and ideally without direct electrical contact. So that poses some technical difficulties to actually imagine it. Well, but recently there have been a breakthrough in the field because there are analogies of fractional quantum Hall effect without Landau levels. Just like in the case of Chern insulator that Houghton proposed. Here, without a magnetic field, you can still use the next nearest neighbor hopping to mimic what happens when you have a magnetic field. And then this was also like experimentally verified that you have this Chern insulator. And if a Chern insulator has partial filling and a lot of interactions, then one can imagine that you might have a fractional Chern insulator. And there have been, despite of the theory that came out in 2011, people have been trying to find the material system to realize it. And at zero magnetic field, one way to realize it, as proposed by Alan McDonald et al. In 2019, is to twist the system. When you add a Moray potential, you might be able to realize it by making a very flat band. And when you are in that very stringent criteria, and you have a Chern number equals to non-zero number, and then 1/3 partial fill of the whole state of a twisted homobilayer TMD, you have all those layer coupling giving you this skyrmion lattice that non-trivial topology as well as strong correlation coexist. And that coexistence eventually led to the observation of fractional Chern insulators in twisted moly telluride. As you can see here, when you tune the displacement field, it only appears, so here, it only appears when the D, or displacement field, is very small. And the displacement field is small means that the two layers are strongly hybridized with each other. And then you can see the quantization is pretty good. And later on, this was also seen in the rumble hydrographin system and so on. So in our point of view, imaging the fractional Chern insulators would be simpler than the fractional quantum Hall effect, just because it has a pretty large gap. From the thermodynamic measurement, it's 7 millieV, that's 70 Kelvin, and also zero fields around 3 Kelvin in twisted moly telluride. We can still see the gap very clearly of the 2/3 gap, for example. And recently, I think Xiaodong's group measured the thermal excitation gap of this material, and the 2/3 gap is around 20 Kelvin. So that all made it much easier, technical-wise, to see the edge state. But of course, we have this advantage of using microwave to measure the edge state. We have the spatial resolution, sensitive to bulk edge differences, and doesn't require direct electrical contact, which is good. But except for the fact that we need a top gate, we need to apply both the top gate and the bottom gate in order to go into that regime of a really small displacement field. And I go back to your question. The top gate would usually screen microwave because it's a metal. Whenever it's a good metal, it will screen the microwave, and the microwave cannot measure anything underneath it. But the trick that we play is to go back to the first project, because we know that monolayer TMD under the excitonic resonances can give us this type of response. And if we excite light at its A exciton, for example here, then you can see in a very large regime, it's pretty insulating. It's pretty insulating for microwave. Then that is the transparency window that we explore and use to make this happen. And once we make the top gate layer transparent enough, which is a monolayer TMD, we can then measure what's going on underneath in the twisted moly telluride sample.
What happens with the reflection
Yes.
from the bottom gate? So it was
Yes.
go in the same place. Or bottom gate is also transparent.
The bottom gate is not as transparent as the top gate.
So what happens with light reflected by the bottom gate? How do you handle that?
The light reflected
So you
back.
sense your waves,
Yes,
and
yes.
everything goes through the top gate, and then
Yes.
some is reflected by your
Sample.
two-dimensional gas, some
Yes.
goes through. But then it hits the graphite gate, and you
Yes.
tell that it's only partially transparent for
Yeah,
this gate.
Yeah.
So
yeah.
some of it's reflected back. How
Exactly.
do you distinguish that from what's reflected from the sample? Or it's a background which you always subtract?
its background.
Oh, I see.
Because we changed it, for example, we can change the bottom gate and top gate, but that shouldn't change the microwave response of the bottom gate. And
But,
yeah,
So what fraction is reflected by the bottom gate?
with
What
refraction.
fraction of the signal is reflected by the bottom gate?
That is very hard to directly quantify because it depends on quite a lot of parameters.
But roughly.
Roughly.
Say 10%, 90%, 5%.
I would say maybe like 50% or less. Yeah, that's the type.
So it's still actually pretty transparent. So these things still have very high resistance at your frequency.
So you're not making the top gate insulating. You're just making it transparent enough, but it can
Yes.
still act like as a gate.
Exactly. Because we still want to have enough carrier density to go to the sample.
Insulators conduct at high frequencies, so in that sense, it's also a regime where this stuff is sort of insulating.
But that works the opposite way you want.
Well, but this is 50% reflection, so it's not exactly metal, but it's not exactly insulator, it's not exactly metal.
But so you're utilizing this
Yeah.
peak, the exciton peak,
Right.
and you're cut off on the gate range. How
Yeah.
much gate range do you have access to?
That's a great question. This is only to a certain extreme, a certain limit. So to quantify it, I would say when it dopes to 10 to the 12th, some prefactor times 10 to the 12th, it just became very conductive, and this gate stopped working.
Which means that this technique has an upper limit in B.
Yes, it has a upper limit. So then what you can do is to choose materials wisely. So you can choose like N-type and P-type TMDs to start with, depending on which region you want to look at.
Got it.
Okay. Yeah. So then with the material in mind, and also with this technique, we can look at what we get here. So these are some very recent transport data, which is what they call is like second generation devices of twisted molybdenum, because apparently like making twisted molybdenum devices is very hard. And then especially if you're doing transport global measurements, you need to make sure that there's no much twist angle disorders and all other things going on. So it's very impressive that they can get the transport data like this. For example, I'm only showing the RXX here, but RXX shows that close to D equals to 0, you can see these like dips dropping down to 0. So those correspond to the FCI states of 2/3, 3/5, and even more. So these are the states. But of course, at higher displacement fields, you can also see states at 1/3, 1/8, 1/2. So these are the charge density wave states. And so we turned out to be very immune to twist angle disorder and also other type of disorders in probing the bulk states. So with our collaborators, Crystal, which was a first generation crystal from Xiaodong's group, and then we stuck at 1.5 Kelvin for that specific measurement, we can get something like this. So here, maximum means very conductive, minimum means very insulating. So the nucleus to -1 is very insulating, at equals to 0, and so does -2/3 and -3/5. So that's a series of fractional Chern insulator with a quantum anomalous Hall states that we can see in MIM, and that is in good correspondence with the transport study. And then another advantage of using microwave is that we can access the part with a lower thinning, or to say closer to the charge neutrality, because in this region, transport becomes very hard, the whole system becomes very insulating. But we have a very good contrast over there. So we can sort of like take a closer look into the -1/3 and the -1/4 states and -1/6. So these are the charge density wave states, but we can also see traces of the -1/3 state inside that lobe. And there has always been the question, like whether fractional Chern insulators has particle host symmetries. I think the general idea is that it doesn't have particle host symmetry because it's a band or lattice-based system. But since a lot of people have saying nu equals to minus 2/3, then whether nu equals to minus 1/3 is a fractional Chern insulator state. So here, since we can measure it very clearly, we measure it as a function of magnetic field. And if it is a Chern insulator state, then according to the Strader formula, it should move, right, with my magnetic field. But what we found was that the nu equals to minus 1 state moved, the nu equals to minus 2/3 state also moved, but the 1/3 state stayed. So we think that the nu equals to 1/3 state is topologically trivial. Okay, and then of course we can also push it into the other regime, the nu equals to minus 3/2 state. And in the very beginning, we saw that at b equals to 0, there was some shaded area. And that shaded area means that there might be something going on over there that's somewhat insulating. So later on, transport showed a more clear nu equals to minus 3/2 state over there, which they explained as an incipient Chern insulator state. And then the Pump-Pro measurement using optics also saw some signatures over there, which might be due to the dielectric environment change. So this is only to show that we have a good agreement with different experimental probes, and when combining them together, they gave us a full picture of what is going on at different fittings. Okay, but then what else we could do was a spatial mapping of the device. So this is how the device looks with twist angle around 3.2 degrees. So here, the scan region is marked as the yellow region, so the yellow rectangular box. And to the left and to the right, these are the two electrodes connected to the sample. And then the sample has a physical edge here, so that's the horizontal blue dotted line. So that's the physical edge of the sample. We also have an interface region without top gate that was not designed, but because of in the AFM cleaning process, it just it just broke. So that region doesn't have top gate. But yeah, anyways, we majorly just look at the flake physical edge. And we first look at the integer quantum anomalous Hall states. What we did was to follow this green arrow to move in this phase diagram, keeping displacement field at 0, more or less, and then change the carrier density. And as we change the carrier density across that region, we map out what the MIM signal looks like. Then as you can see here, as we change the nu, it goes to very conductive everywhere, to gradually only the edge is conductive, but the bulk becomes insulating. And then
what is the white
yeah.
bar? How long is it?
That's 1 micron. And then we keep going to -1, -0.95, and gradually the totally conductive feature comes back once again. So that is in accordance with what we shall see when you have a quantum anomalous Hall state because of the bulk edge correspondence. So you'll see a conductive edge. Then we went into the fractional fitting states. And here we go through the nu equals to -2/3 and -3/5 states by moving on the space diagram. And we do it again. So as you can see here nothing develops. Okay, and gradually, when it approaches -2/3, this conductive edge and insulating bulk behavior comes back. And then similar things happen for nu equals to -3/5 stage.
So this figure is not inverted, right? So what you have,
Yeah.
the right conductive region corresponds to the interface and not to the flake edge.
This is the flake edge.
Oh, so
So
that's
where?
rotated 90 degrees.
Yeah. Here. This is the edge. But it's not rotated.
Oh, it's not
Right.
rotated.
Yeah. So
Oh, I see.
this is the edge. Yeah.
Okay,
And
so
that
you
is
say
the
they don't
edge.
have the same orientation.
Right.
Right.
So what you're telling is that the edge is always wider at the interface and more narrow at the flake edge.
Yeah.
It's about the same.
Yeah. Sorry.
No, it's a comment. It's not a question.
Oh,
It's about the same.
oh, it's about the same. You mean this width and that width?
Like if you look at -0.69,
Yes.
you can tell the edge on the right and the edge at the top is about the same. Right? The interface is clearly visible there.
So I would say that this interface is probably not the interface that you're normally thinking about, because here we don't have control over the two sides simultaneously. So then that interface is more or
I
less
see.
like out of control. Like where it is at is mostly determined by what backgate voltage we are
So on
applying.
the right hand side, there's no top gate.
So it's only this stripe. We don't have top
I
gate
see.
here.
I see.
And we have top gate there and there. So yeah.
Right.
But David,
Yeah.
so the density is not actually minus 0.6 in this interface region. It's something very
Right.
complicated.
Yeah. It's
And
very-
that's why
something
it
very
becomes so
complicated.
broad. So it's not necessarily the edge. It's
No.
just that you don't know what your density is.
Right.
And the actual edge is only on top.
Yeah.
And it's not as
Very
wide.
true.
Okay, that's
But
actually
so on
very
the-
helpful.
But on the previous slide, it looked like these edge states are much more narrow.
I think
Maybe
that
I'm confused.
I think I will show the slide comparing the edge
Okay.
width of these three states,
Okay.
so you can see clearly the line cut of the edge. Yes.
Okay, so the edge actually is more narrow than focusing on this interface, because this yellow region corresponding to interface is very visible. It looks like that the edge is enormously wide, but the true
Right.
well-controlled edge on the top, and it's not that wide.
It's still wider than we thought, but I agree. It's not as wide as the interface region. Yes. Okay. So after saying those features, we went into considering what is that signal telling us. So one fact check that we did was to stay at equals to minus 2/3 carrier density, and we just changed the displacement field. Because changing the displacement field in the FCI in the twisted mode telluride will drive us from FCI to a Chern density wave state. And we want to see whether that edge signal, which could be coming from some sort of disorder at the edge, are still there. So then this is what we did. As we change the displacement field, as you can tell, at very large displacement field to either side, the sample just became very insulating everywhere. But it's only when we are at small displacement fields we could see the contrast between the bulk and the edge. So it means that the edge has something to do with the topological state underneath. And so we also did some measurements of the spatial homogeneity of the sample. And it seems like it is a very nice sample, that the spatial homogeneity is around maybe less than 5% of the twist angle. And so that allowed us to see this more bulky type of phenomena where well-defined edge is there. But we could also see that if we drive the system too close to that topological phase transition with displacement field, that homogeneity is no longer there. So that whole phase transition process is very complicated. I've learned a lot of like the percolation theory and everything about the quantum Hall effect, which might be more complicated here because it's a transition into a transcendental wave. So yeah. But yeah, so back to your question, the nature of the edge signal. We did a line cut here. So this is a red, white dashed line. We cut through there, and then we see what is the width of the edge and also the signal at the edge. So what we see is from nucleus to minus 0.8, which is a metal in a way, where some people call it anomalous Hall metal. But regardless of that, this signal just rises up and becomes some constant value throughout the book. But here, when we go to nu equals to minus 2/3, it first rises up even higher and then drops when it goes inside the book. So it's a process that gives us even more microwave signal at the edge than what we can get when it's a perfect metal. And that increase, and also we observed a different feature, which is that the width of the -1 and -2/3 and -3/5 are very similar to each other. And then they're pretty broad. So they're not super broad, but if you calculate the half-wave maximum, it's around like several hundred nanometers. And so we went into
total size of the sample is
several microns, like 4 microns.
What's
Yeah.
the magnetic length?
The magnetic length is super small. That's on the scale of 10 nanometers, determined by the twist angle.
and
Yeah.
the distance to the gate is 60 nanometers.
60 nanometers.
Okay,
Yes.
so it's still another point of model than distance. Okay.
Yes, yes.
What's the Moray length scale?
It's more than scale 10 nanometers. Yeah, and so we went into we also wanted to know why this is so wide. Our first impression was that maybe it's a tip resolution, but we checked in the bulk part of the sample, and the tip resolution was clearly better than this. It's less than 100 nanometers resolution because we could resolve features less than that size. But then there was a theory going out talking about from Tiger and al. In 2023, talking about what microwave impedance microscopy is actually measuring when it hits a Chern insulator edge state. And it says it's actually measuring the edge magnetoplasma. And that maps onto the reassuring very early measurements of gallium arsenide in the microwave regime. You will see the edge magnetoplasma. And the edge magnetoplasma has many resonances depending on a lot of things. And for example, here we are at the smaller frequency regime. So we are mostly probably seeing the first resonance of edge magnetoplasma. And then, for example, its resonance frequency has to do with the sigma xy, or somehow has to be related to the charge. And also the characteristic of width of that magnetoplasma is 1/k. And that has to do with the velocity of your modes, your frequency, or to say the perimeter of your sample. So I had a lot of discussion with Dima, and it turns out Dima also came up with this theory, separately. So that's a very good blind check that we agree upon this theory. So that means that we are not directly seeing the edge conductivity. That is a little bit of disappointment, but also because this type of resonances are giving us information in a different way of the sigma xy and sigma xx, so we can still extract information out of it. So we can also compare to previous studies because microwave has been used for measuring quantum Hall effect, quantum spin Hall effect, and quantum anomalous Hall effect. All of those edges are wider than we thought. So it couldn't be a sample quality problem that's so systematic, and that will all contribute. Can be attributed to this type of plasmonic resonances. Yeah, but we do want to get more information out of it. So technical-wise, we have been making some progress. So because we want to go to higher frequency, the higher the frequency is, the narrower it gets, and also we want to be able to tune the frequency such that we can see the resonances very clearly. And that will give us 2 axes. So recently we've been able to make some tunable cavities, silicon photonic cavities. We put a sample onto it, and then this is a 2D sample made onto it. And then we measure the topography. So this is still a trial sample at room temperature of graphene and HBN. But we can see very clearly these boundaries of graphene and HBN, so we can see the conductivity contrast there. But this is at frequency of 90 gigahertz, so millimeter wave MIM. And that can potentially, we would like to bring it down to low temperatures to measure those systems again to see what we can get out of it. Okay. And back to the edge picture. So then what the signal is telling us is actually two parts. One part is the bulk residue conductivity, and the other part is edge mode magnetoplasma. So we're to see this part has to do with sigma xx, this part has to do with sigma xy. We can first assume that the edge is just like a very simple 2/3 edge with a conductivity, right? And then what we can, so we can then calculate what it means for different states, -1, -2/3, -3/5, because we know sigma xx in the book, so we can see what is the relationship between them. Similarly, we can do this because we can calculate through the charge the resonance frequencies of these. Then compare with our results, and we found that there are discrepancies between this calculation and the actually measured magnitude of MIM. And that shows some deviation from the model. So our conjecture would be that it is actually mapping onto the Kane-Fisher-Porchinsky model very well, because in a very old paper, they mentioned that this type of edge scattering could lead to a charge mode that propagates with a different dispersion, with a different diffusion constant that is absent in the quantum Hall edge states, where there's no like inter-edge scatterings and disorders going on. And in fact, because our sample is a physical edge, there are supposed to be a lot of disorders going on at the edge. So we would love to explore more into the correspondence between our results and this picture. And also, although this is by mistake or accident that we lose this top gate, but we could see something happening. We can manipulate the top gate a little bit to achieve some imbalance of this doping and that doping. And we can see the coexistence of FCI domains on the left-hand side and the right-hand side. Although this interface is not a topological interface. But yeah, that gave us some hope that maybe one day one can use FCIs to do similar things that people have been doing with fractional quantum Hall effect. And yeah, because I just went to this FCI workshop, and now people are concerned about the nu equals to -2 state. Is it a quantum spin Hall state, or is it a Chern insulator state? Actually, theoretically, there have been quite a lot of theories talking about different possible ground states of nu equals to -2. Because nu equals to -1, one can think of it as just having one of these valley polarized bands. So that's relatively easy to guess. But then for nu equals to -2, because there are two valleys, they could be balanced, they could be imbalanced, so there could be different compositions of nu equals to -2, leading to different ground states. So then we measured this nu equals to -2 by pushing our top gate to very, very, very high doping densities, and it seems like it's still working pretty well over there. And then going through this arrow, we measure the edge state. So it seems like whatever happens at nu equals to -2 is very different from what we saw at nu equals to -1. You might argue that there's some big signatures of things lining up at the edge, but the width is very small. And also, it seems like the sample becomes very inhomogeneous at nu equals to -2. It's still the same piece of sample, but somehow that just happens. We're still trying to understand like what is going on over there. Or is that a competition of phases, or what is contributing to this? But yeah, more than that, because this is a local probe technique, we have the natural advantage of searching for states that's relatively more fragile. So we cooled down the sample even more to 500 million Kelvin, which is not so much compared to transport like Leo does. But we're trying to cool it down even further into a dilution fridge, not yet. And then we saw that at specific points of that sample spots, we just like scan through the whole sample, and we can see at nu equals to -1/2, there is a small dip. And this happens at maybe 3/20 spots in that sample. So we are not able to conclude what that is yet, but at least the nucleus minus 4/7 was very apparent. And also it seems like the nucleus minus 2/5 could also be there. So actually this shows a pretty good particle Hall symmetry across nucleus minus 1/2 for some reason. So we're trying to still digging into that. But yeah, if we can see something like nucleus minus 2, that would be the signature of the non-abelian physics and other things. But that would need a higher sensitivity into the more conductive regime. Once again, this millimeter wave MIM would help us because the x-axis is rho times omega. So that would push us into this more conductive regime. Okay, and here comes the summary. We have this optically coupled MIM sort of setup. And then that allowed us to image the fractional Chern insulator edge states in a form of edge magnetoplasma. And then it is also a very sensitive local probe of the FCI bulk states. There are a lot of open questions that we're still exploring, including the even denominator states and composite Fermi C, magnetoplasma's resonances, and including the fractional charges as we discussed today. So yeah, we're still on the road. Thank you.
I'm a little bit confused. So is the edge magnetoplasma a gapped excitation?
It's not.
Because
it's 1D.
Because earlier you said that this doesn't work for a semi-metal, right? If you start coupling in for like graphene, for example, you're gonna not see signal. But then here you're coupling into the magnetoplasma, which is gapless, and so I'm confused why it doesn't cause a problem here when it does for graphene.
Oh, for the graphene case, you can see signal. The problem is like on top of the semi-metal, if you have more excitons, whether you can see signal change because of that. Because I assume that the carrier density change because of the excitons is not that significant. And if you start with something that's already very conductive, like you're over here, right? Then it doesn't change much. So because like the contrast is important. Versus here, the bulk is pretty insulating. And then if there's the edge magnetoplasma, which is gapless, then we can directly see the contrast between the edge and the bulk.
I see.
Yeah.
The questions? Can I ask a question?
Yeah.
So you mentioned that when you considered minus 2 thirds, the Little's edge was 700 nanometers. So what is that when I knew it was minus 2?
The
You
nearest
showed
to
a much
minus
more
2.
narrow
Yeah,
picture,
it's
but
much.
what's the actual width is?
This actual width is on the order of maybe 200 nanometers.
Oh, so it's the
Yeah.
same edge width as normally expected on gallium arsenide samples. It's
Right.
the
So
same
it's a
exactly
very-
distance to the gate.
Right.
3 times more than the distance to the gate makes sense, but why would you switch from long range to short range vision?
Right. So I was talking about the nucleus minus 2 state. If we stick with the magnetoplasma picture, if we assume this is an edge state, not something else, then because here the perimeter becomes very small. If the coherence length of the quantum small edge state is very small.
What is the gap?
The gap.
How do the gaps differ between minus 2 thirds and minus 4?
That's a great question. I think the field still has some debates about the gap at nucleus minus 2. So yeah, no one has a very clear answer for that question yet. There's still debate about like whether there is a gap at nucleus minus 2.
Is that the one King-Fi report?
Yeah. So yeah, because you can see there are different types of ground states over here, and then not all those ground states are meant to have gap.
So it is so that it's more efficient in killing everything here because the gap is so
Yes.
much lower.
Yes,
And
that
maybe-
could be the case, explaining why the spatial
Yeah,
homogeneity.
it's still surprising. You have
Okay.
extremely high frequency, but
Yeah.
maybe indeed these are relative things. It's not like it's black or red. So maybe
Yeah.
maybe you just localize stuff and it compresses
the edge. Ultimately, the more disorder, the more narrow the edge. That's the standard picture, both statically and dynamic. Maybe it's just more sensitive to disorder at miracle minus 2.
That would actually make sense if the gap is very small. Yeah.
Yeah,
Thank
it's
you
very
for that.
interesting, it's very
I'd like
interesting.
to talk to you
So
more.
have you published this anywhere?
No, not yet.
Yeah, so that's extremely interesting.
Thank you.
Other questions?
Yeah.
I'm wondering if there are any ideas to extracting the velocity, charge velocities.
Yes.
Yeah.
So if we can measure the spectrum as a microwave frequency, we can directly get the velocities out. We're trying in progress.
Speaking of that, there is a clear tension between thermodynamic picture and actual solution of equations for magnetoplasma. Say, when you think of neutral one edge, you know that there is exactly one mode that contributes to thermal conductance, and when you write down a field theory describing the edge, you have exactly one mode on it. And yet there is a solution of magnetoplasma equations by Glassman and Arlena showing an infinite number of chiral modes. There is always a tension between these two things, but we do know that there is a leading mode and a bunch of other modes with a relatively high imaginary part of energy. And apparently they just somehow emerge from a model that truly has a single mode. And I wonder if you have access to the second thing. You just mentioned that you can see this IDQ square that's predicted for the charge mode and the Kane-Polchinski picture. Perhaps you can see the bulk of the bunch of all these modes that Arlena and Glassman predicted. They are similar to that, just there is an infinite number of them in principle.
That's a great question that I don't have a good answer now. I mean, as you just mentioned, there's no very good picture of the magnetoplasma for very complicated edge state.
The thing is that as the mode discussed by Kane, Fisher, and Polchinski is still hydrodynamic mode.
Yes.
And the modes discovered by Arlena and Glassman apparently are not